All right, so the next phase of this project then is to understand various aspects of Coulomb gauge within classical electromagnetism. And in order to do that, I need to make a digression into a technical subject, which is namely that of transverse and longitudinal vector fields. This is something which I don't know whether it's covered in 209, but I'll go over it anyway, go over the parts of it we need. So let's put the Maxwell's equations and the general project on hold, and let's make a digression into this general subject of transverse and longitudinal vector fields. So the kinds of vector fields in real space that we're talking about, I'll call F to stand for any of them. Let's call it F of X. These are normally real vector fields, you know, electric, magnetic fields, and so on. So F is equal to F star. We'll assume that for the vector fields that we'll be using, we'll assume that they're real in real space. We also want to write them as Fourier transforms, so let me give you my convention for a Fourier transform. F of X is given as an integral over K, 2 pi 3 halves e to the I k dot x. This is just convention for Fourier transform. And I'll call a Fourier transform with a tilde. It's F tilde, it's a vector, and it's a function of K, and the tilde just means this is the Fourier transform. So the Fourier transform F tilde of K, or let's write this as the inverse Fourier transform if you prefer, is an integral over X divided by 2 pi 3 halves of e to the minus I k dot x times F of X. So this is a forward and inverse Fourier transforms, just giving a convention for the normalization which balances the factors of 2 pi between the forward and inverse transforms. All right, so let's make these definitions. So the first thing to say is that if F, even if F is real in real space, X space means real space, the Fourier transform is not real. It's really a complex field on K space. But it's not an arbitrary complex field because of the reality condition in real space. And in fact, the reality condition in real space, it can be shown rather easily. This implies that in K space you have the Fourier transform at a value K in K space is equal to the Fourier transform at the opposite value of K, complex conjugated. And this is sometimes called a crossing relation. And you need to use it if you want to take into account the reality in real space. All right, so this is a definition then of the Fourier transforms. One of the consequences of these definitions is the Parseval identity. And not to be confused with the opera by Wagner, which is spelled differently. The Parseval identity is that if you integrate over all of real space, two vector fields, let's call them F and G dotted into each other, that you get the equivalent integral over K space, except in K space the fields are complex. So it's F tilde of K, and you need to star it, dotted into G tilde of K. So what you have here is an obvious kind of inequality of the scalar product of the fields in real space and in K space, which is what works out in detail with these balanced coefficients and Fourier transforms. All right. Now, I'm going to run out of room here pretty soon, and I'll switch back over to the other board and warn you. But in any case, let's draw a picture of K space here, Kx, Ky, and Kz. And let's draw in like a typical K vector that's sticking out here somewhere like this, K vector. And at the tip of the K vector, let's sketch in the plane in K space, which is perpendicular to K. So if we continue this vector on out like this, we get a perpendicular like so. Perhaps I should have drawn the plane bigger, make more room for what I need to show. Now, if I have a vector sticking out here, call it F tilde in K space, I can decompose it into a component which is parallel to K, which I'll call F tilde with a little parallel sign on it, and a part that's perpendicular to K, sticking out like this. Let's see if I draw my diagram, it's going to be something like this. Like so. This is, let's call it F tilde perp of K. And this, I better erase Parseval because it's getting in the way. Let me take that out. Getting in the way of the diagram. So this is just decomposing a vector at a point K into its part which is parallel to K. This is called the longitudinal part. And the part which is orthogonal to K is called the transverse part. In other words, the terms longitudinal and transverse really apply to K-space, is the terminology here. And so by doing this, we can obviously take any vector field in K-space, F tilde of K, and we can decompose it into a longitudinal part in a unique decomposition like this, plus a transverse part in a unique manner. The longitudinal part, if I can write it up here, it's easy to see what it is. F longitudinal of K is given by K hat times K hat dotted into the full F tilde of K like this. Just project out the component in the longitudinal direction, multiply by the unit vector in that direction. Anyway, that gives you the longitudinal projection. If you want the transverse projection, what you do is you can just subtract the, so what this means is that the operator K hat is the longitudinal projector. If you want the transverse projector, you just have the identity minus K hat, and that takes care of the transverse projection. Okay. So this is the concept of longitudinal and transverse vector fields, and the point is that the terminology is all based on what goes on in K-space. Now, however, if I take this decomposition and I Fourier transform back to real space, I will write this as f of x, the original vector field, is f longitudinal of x plus f transverse of x, where f longitudinal and f transverse in real space are defined by the Fourier transforms of the corresponding decomposition in K-space. So if you want to know what for example, if you want to know what f longitudinal in real space is, if you're given the original field f, one way to do it is to Fourier transform into K-space, project out the longitudinal part, and then Fourier transform back. And in a similar manner, you can do this for the transverse part. Now, let me erase this crossing relation to make some little room here. Here's just some things to note, is that in K-space, the K crossed into the longitudinal part of the vector field is 0 because the longitudinal part is parallel to K. And likewise, K dotted into the transverse part of the vector field in K-space is also equal to 0 because the transverse part is perpendicular to K. On the other hand, the gradient operator in real space goes over into IK under Fourier transform. And so what this means is that the longitudinal part in real space is a curl-free vector field. Del cross F longitudinal is equal to 0. And likewise, the divergence of a transverse vector field in real space is equal to 0. And what this means is that when we do this decomposition of our vector field in real space into its transverse and longitudinal parts, we're in effect taking a quote-unquote arbitrary vector field in real space, and we're decomposing it into two terms, the first of which is curl-free, and the second one is divergence-free. Now I say quote-unquote arbitrary because in order to make this, if you want to make this a rigorous mathematical theorem, one of the things you need to do is to require that these fields die off at infinity rapidly enough, go to 0. And I will be implicitly making those assumptions that make this whole formalism work. But with that understanding, the arbitrary vector field within that class of vector fields, this is true that it can be broken up uniquely into a divergence-free plus a curl-free vector field. Okay, so this is some of the basics then of longitudinal and transverse vector fields. I think there's one more point that I want to make, but I'm running out of room over there, so let me do it over here. One more point about longitudinal and transverse vector fields, and it is this, is that, it's actually several more points. Here's one of them. One of them is this, is that if I have a vector field in real space which is longitudinal at some point x, and I have a second vector field G, which is the transverse part of G, let's say like that, form this dot product. There's nothing special you can say about that dot product. The reason is that the longitudinal and transverse stuff applies to what goes on in K-space. And if you're evaluating F parallel and G perp at a given point, it mixes up, the Fourier transform is mixing up values from all over K-space. There's nothing special to be said about that. On the other hand, so in particular, it's not zero. On the other hand, if I integrate this scalar product over all x, then by the Parseval identity, this goes over to the integral over k of basically the f longitudinal in K-space dotted into G transverse in K-space, like this. One of them is a star on it, like this. And this is equal to zero. It's equal to zero point-wise in K-space, so the whole thing is equal to zero. So there's a kind of an orthogonality then between longitudinal and transverse vector fields in real space, which is that if you integrate, you get an answer which is zero. This will be useful later on when we manipulate the Lagrangians and Hamiltonians for the field. All right, let's see. Here's another aspect about longitudinal and transverse vector fields. Let's look at a transverse vector field in real space, that transverse of x. So the question I'd like to pose is, suppose I'm given the original field f of x, and I want to find f transverse of x at the same point. Well, it turns out it's not as simple as it looks. There's no simple relation in which there is no way to go from the value of f at a given point to the value of f transverse at the same point. Again, it's because Fourier transforms are non-local. The relation between the transverse component of the field and the original field is a linear relationship, but it's not a local one. And so what that means is that f transverse at a given point x can be represented as an integral transform. Integral over d cubed x prime like this, with some kernel that I'll call capital delta sub per. And I'll put a double integral over it because it's really a tensor. It's a function of both x and x prime. And this is dotted into f of x prime. Now, all I've done here is just to create a linear mapping, a linear integral transform that takes the original field into the transverse component of it. But the result is that this integral transform is a kind of a projector. It's being expressed now in real space. And the kernel, as I mentioned a moment ago, is actually a tensor. This kernel is sometimes called the transverse delta function, although it's not, as I keep saying, it's actually a tensor, not exactly a scalar function, but it's called a transverse delta function, and it's useful to have some expressions for it. And so I'd now like to show you how we can get one such expression. It's really a direct application of the definition. If I start with a vector field, let me write it over here to the right, give myself enough room. Let's write f of evaluated at point x prime. Suppose this is a given vector field in real space. If I want to project out the transverse part, the procedure is Fourier transform it, do the projection in K-space, and Fourier transform back. So to Fourier transform it, what I want to do is multiply it by e to the minus ik dotted into x prime, and then do the integral d cubed d cubed x prime divided by 2 pi 3/2. Then I want to project out the transverse part in K-space, which is identity minus k hat, multiplied onto this vector that is produced there, and then Fourier transform back, so I multiply by e to the plus I k dot x, like this, the integral d cubed k, divided by 2 pi to the 3/2. I'm just stacking up the transforms needed to follow the rule, and this gives me f transverse at field point x, using the definition. And so now, if I want to read off what the transverse delta function is, it's basically this whole formula here, except I strip off the x prime integral and the f of x prime. Here's the f of x prime right there, and here's the x prime integral right there. I'll leave off the denominator, which is not part of what we're removing. So I just remove the circled parts here and rearrange it slightly. And what you get then is a delta perp of x and x prime is equal to an integral over k space. That k integral remains, you see, d cubed k divided by 2 pi cubed. There's two factors of 2 pi to the 3/2. There's an exponential, it's e to the ik dotted into x minus x prime. And then all that's left over is the identity, the projector in k space, identity minus kk, and this is what we get. This is a useful expression for the transverse projection operator. So that operator will be used in a homework problem involving understanding retardation and Coulomb gauge. Now, I want to mention another version of the same transverse projection operator as this. I'll write it in index form now. Delta per ij of x and x prime, writing up the components. It turns out that this thing can also be written in the following form, which I won't prove in class, although the proof is actually given in the notes. It's minus 1 over 4 pi. It's delta ij. There's a del squared Laplacian operator minus derivatives, delta second derivatives xi, xj. And then this all acts on the Coulomb denominator, 1 over x minus x prime, like this. And this is another expression for the transverse projector, which one can show is actually identical to this one. It's just written in a different way. In fact, perhaps you can see that the del squared here acts on the Coulomb denominator and gives you a Dirac delta function of x minus x prime. The delta ij here is really the same as the identity tensor here. If you just concentrate the identity tensor term in this expression for the transverse delta function, that's independent of k, and so can be taken out of the integral. What's left over is an expression for the Dirac delta function of x minus x prime. It's the same thing you get by Laplacian acting on this Coulomb denominator. So you can see how there's at least the del squared term and the identity term here are the same term. By the way, the transverse transverse delta function written in this form is something we've seen before in the course. In fact, the magnetic field for a magnetic dipole, point dipole, we looked at when we were doing the hyperfine effects, has exactly this form. That is to say, the tensor is multiplied into the magnetic moment to produce the magnetic field vector. And the tensor in question that one is multiplying is exactly this one. The del squared times the identity part, the del squared gives you a Dirac delta function. Those are the Fermi contact terms that came out of the analysis of the point dipole. So anyway, that's just a remark that we've seen this before. All right, I think that's all I want to say about the machinery of transverse and longitudinal vector fields, which has all been fairly general. However, allow me to comment on how this machinery gets applied to the equations of motion, these versions of Maxwell's equations that we're using in Coulomb gauge. Let me return to the equations of motion. So in the first place, Coulomb gauge itself tells you that in Coulomb gauge that the vector potential is purely transverse. Now, usually I'll leave the perp sign off and it'll be understood that A is transverse. But this is part of what, this in fact is the definition of Coulomb gauge, is that it's purely transverse. Divergence free means the same thing. If we look at the manner in which vector potentials change under a gauge transformation, gradient of chi like this, one remark is that the gradient of any scalar, let me call it that, if you take the gradient of any scalar, this is always purely longitudinal. We know this because if you take the curl of it, you get 0. So grad f is always longitudinal. Also, if I take the curl of any vector field, call it capital F, this is always transverse because if I take the divergence of that, I also get 0. So the curl of an arbitrary vector field is transverse and the gradient of an arbitrary scalar is longitudinal. So in this part of the gauge transformation, what you can see is you're taking the old vector potential and you're adding a new part which is purely longitudinal. This is going to change the longitudinal part of A, but it won't change the transverse part, which is all there is in Coulomb gauge. And in fact, the gauge transformation that would take you from an arbitrary gauge to Coulomb gauge is finding the right chi to cancel out the longitudinal part of whatever A you started with, leaving behind only the transverse part. So there's a certain point of view which emerges here, which is that the physical part of A, quote unquote, is the transverse part, and the longitudinal part is the non-physical part, the part that changes under a gauge transformation. Now, I don't want to push that statement too far because it's not coherent. It only works in a given frame. So you'd think logically if something were physical in one frame, it'd be physical in another. So that indicates flaws with this line of language that I'm using, but still it's worthwhile thinking about it all the same. All right, in any case, Coulomb gauge means that A is purely transverse. Now, the magnetic field, of course, is del cross A, so that means that the magnetic field is also purely transverse, always. There's never any exceptions to that. The magnetic field is transverse. What about the electric field? It's minus gradient phi minus 1 over C dA dt. If we work in Coulomb gauge, then the second term is purely transverse, because A is purely transverse. That's what Coulomb gauge does. Meanwhile, the first term, being the gradient of the scalar, is purely longitudinal. So working in Coulomb gauge, these two terms are precisely the decomposition of the electric field into both into its longitudinal and transverse components. And now, if I may go back to the electrostatic model, the electrostatic model would involve using a non-retarded phi obtained, probably erased it, no, it's right over there. It's a non-retarded phi based on the charge distributions. Making this phi, notice, now becomes a function of the matter degrees of freedom. It's not an independent dynamical variable. It depends on when the matter determines the charge density. And so likewise, its gradient is also a function of the matter degrees of freedom. This is what you get out of Coulomb's law for electrostatics. What I've been calling the electrostatic approximation involves replacing the full electric field with E longitudinal and ignoring or setting E transverse equal to 0. As we'll see, the light waves and emission and absorption of radiation is all contained in E transverse. So this is some of the insights you get with this notion of longitudinal and transverse vector fields and applied to Maxwell's equations in this form here. All right. Now, okay. Now the next thing I need to do is to present you with another somewhat technical topic, which is box normalization. We've of course seen that before, so some of this is repetition. But I want to go to box normalization because the electromagnetic field, being a field, has an infinite number of degrees of freedom. This is characteristic of fields. In fact, then arises a question about whether the degrees of freedom are continuous, and whether they are, there's two kinds of infinity. There's continuous infinity and discrete infinity. And the question is, which is it? Well, it's more convenient mathematically if we make the infinity discrete, and we do that by using box normalization. So for mathematical convenience, we're going to do that now. So, as we did before when we were doing scattering theory, we imagined dividing the universe up into cubical boxes whose psi is equal to L, whose volume therefore is equal to L cubed. And we assume that all physics, both fields and matter, are periodic in the boxes. Ultimately, we're going to let the size of the box go to infinity, so that won't matter. If we have a function S, let's say S of X, S stands for a scalar, so it won't have a vector over it. And we have a function S of X, which we assume is periodic, then it can be expanded as a Fourier series, meaning it's the sum over discrete k vectors of Fourier coefficients S and k times e to the I k dot x. And the k vectors which are allowed are, as we saw earlier in dealing with box normalization, are 2 pi over L times an integer vector n, where that's got 3 components nx, ny, and nz. And each of these 3 components runs from minus infinity to plus infinity through 0. It includes all integers, positive, negative, and 0. This gives us the allowed values of k, which are consistent with the size of the box, the 2 pi over L connection with the size of the box. This means that in k space, if I draw a picture of k space, kx, ky, and kz, we have not a continuum of k values, but a lattice of points like this. It's a cubical lattice. And the dimensions of the cube in k space is 2 pi over L, like this. As we let L go to infinity, the density of points in k space goes to infinity, and we go over to the continuum. And in any case, the density of points in k space, of k points, is just equal to the inverse of one of these cubes, these k cubes that you construct here. which is 2 pi over L cubed, so the inverse is L over 2 pi quantity cubed, which is equal to the volume divided by 2 pi cubed. Sometimes we call this a density of states, but I don't want to call it that because sometimes there's more than one state attached to a given K point, as we'll see is the case with the electromagnetic field. So I'll just call this density of K points or points in K space. But in any case, this is what it is, it's V over 2 pi cubed. To go back to the Fourier series then, so the K values run over the lattice, this is a discrete sum now, and they run over the lattice of points, infinite lattice of points, but discrete sum in K space. Now in writing this Fourier transform for our periodic function, it's actually convenient to split off a factor of 1 over the square root of the volume of the box from the Fourier coefficients S of K because it makes for neater formulas. And in particular, the inverse transform is that S of K is equal to 1 over the square root of the volume of the box, and integral over the box, d cubed x of e to the minus ik dot x times s of x. And so this is the backwards. So when you have periodic boundary conditions, you end up with Fourier series instead of Fourier integrals, and this is some of the formalism of the Fourier series. Now, we will ultimately be interested in the limit where b goes to infinity. And if we do this, one can work out some rules for how to make the transcriptions that will take you from Fourier series over to Fourier integrals. And so let me summarize these for you. These will be of use later. In the first place, the sum on K gets replaced by the density of states in K space, which is right here, volume over 2 pi cubed, times an integral over K. That's what happens in the continuum limit. Likewise, you'll find that the Kronecker delta, kk prime, you see when you're dealing with Fourier series and the K points are discrete, you have Kronecker deltas of different K values because they're discrete. It's 1 or 0, depending where the lattice points are equal or not. But in the limit, this goes over into the quantity 2 pi cubed divided by the volume V times the Dirac delta function of K minus K prime. This is just a formal substitution, which with more time I could justify for you, but I think you can work these kinds of things out for yourselves. In any case, this is a substitution you want for the delta functions. And then finally, the S of K, the Fourier coefficients, go over into 2 pi to the 3 halves divided by the square root of the volume times the Fourier transform, S tilde of K. If you make these transformations on these formulas here, you will see it reproduces Fourier integrals, series turns into integrals. All right. And likewise, the Parseval identity and things can be written now in terms of Fourier series instead of Fourier integrals. I won't go over the details of that because it's pretty straightforward. Okay, so that takes care of another small piece of technicalities that are needed to do this project. Let's go on to the next stage. The next stage is to worry about actually solving the Maxwell's equations now that we've got the gauge, the transverse and longitudinal aspects, and the box normalization taken care of. I can do this over here. We're going to do this in 2 steps. The first one is to take the simple case of the free field. Free field, of course, is one in which there is no charge density and no current density, so these 2 terms will disappear. So let's take that case first and look at what's involved in solving the equations of motion. Of course, physically speaking, if you have a free field, there's no matter around, there's no charges or currents. So the only thing the field can be doing is propagating light waves moving around in an infinite vacuum. That's the idea. So let's take the free field. Rho equals 0 and J is equal to 0. And so then the equations of motion, as you see from over there, if I make these substitutions on rho and j, so we get del squared phi is equal to 0, we get del squared a minus 1 over c squared b squared a t squared. The wave operator acting on the vector potential is equal to 1 over c d t of gradient phi, like that. Now on the other hand, if del squared phi is equal to 0 everywhere, and phi goes to 0 at infinity, as we assume, this means that the unique solution is that phi itself is equal to 0. This is really just Coulomb's law, in which rho is equal to 0. You see phi has to be equal to 0. And so the right-hand side of the vector potential equation also becomes 0, and we just get a simple wave equation for A. But let's remember that we're working in Coulomb gauge, so the divergence of A is equal to 0. All right? So to solve these equations, we just need to solve the wave equation for the vector potential, now purely transverse vector potential. If we wish a wave which is traveling in the direction k with a frequency omega, it has to be proportional to e to the I k dot x minus omega t. This is complex, of course, and the vector potential A is real, but I'll come back to that in a minute. In any case, the space-time dependence needs to look like this if you want a plane wave moving in direction k. And moreover, the frequency has to be given by c times the magnitude of k, which I'll write as c times k without an arrow over it. And sometimes I'll write it as omega of k, omega sub k, if I want to emphasize that the frequency depends on k. In fact, in almost all of this discussion, the frequency will be understood to be a function of the wave vector k. This is, of course, just a dispersion relation for vacuum light waves. So A is going to be proportional to this. Now, A is a vector, so we need to multiply this by some constant vector. I'll call it C0, like this. And then this is then as a solution, because the solution is taking of x and t. For a light wave moving in direction k. Now, it has a problem, though, because A is real, and to fix that up, I'm going to add a complex conjugate to this. And if we do it, then the right-hand side is real. Now, if we allow this vector C0, which appears here, one other remark is that because of the transversality condition on A, the vector C0 has to be transverse, so k dotted into C0 is equal to 0. So although k has nominally three components, there's one of them is forced to be 0 by the transversality condition. So it really only has two independent components. Now if you allow this C0 to run over all complex vectors which are transverse, if you analyze this equation a little more carefully, you will find that this generates all possible electromagnetic waves that have the given k vector. In other words, it's a complete set of solutions with a given k vector. But you must allow the vector C0 to be complex. You can't restrict it to be real. For example, if you want the x and y components of the vector potential to have different phases, then you could make, like, say, pi over 2 out of phase. Then the complex number in the x component here and the y component should be out of phase in the sense of complex numbers by an angle of pi over 2. That's necessary. You need this. You need the complex numbers in order to get a complete set of solutions. All right, even though A is real. So this is a solution with a given direction k. If we want the most general solution of the wave equation, transverse solution of the wave equation, we simply sum over all possible k values on our lattice of points in k space and allow this coefficient vector to depend on k. And that's what I'm going to do, except for one more cosmetic change. I'm going to remove the factor of the square root of volume from the coefficient, because that turns out to be convenient, and that was also what we were doing in Fourier series over there. And the result is that I've now written down the most general form for a vacuum light wave, decomposed into subsets that have subcomponents that have different k values. Okay, what I'd like to do is to analyze this equation further to develop in some detail the notion of the modes of the electromagnetic field. And I think if I do that before the end of the hour, that'll be a good accomplishment. So this is the start of it. The next stage in the analysis of this is to introduce some definitions. Allow me to introduce the vector C sub k. Well, to back up a little bit, the most general solution, as you can see, then of the vacuum Maxwell equation, most general transverse solution, is obtained by choosing arbitrary complex vectors for each k point each lattice point k in k space. That gives you the notion of the set of such solutions. Those are independently chosen complex vectors. At two independent complex numbers because it has to be transverse. Now, allow me to do this. Allow me to define a vector I'll call c sub k, which is a function of time. And it's given by c sub k, or c sub 0k. And it just captures the time dependency of the minus I omega t from these light waves here. And with this simple definition then, what I've got is that A of x is 1 over the square root of volume V, sum on k, c sub k, times e to the I k dot x, plus complex conjugate. And now the c sub k's have a dependence on time, the A does also, but it's captured by the time dependence of these coefficients. The time dependence is also described by an equation of motion for the c's. If I just differentiate, this gives you c sub k dot is equal to minus I omega c sub k. This is the equations of motion of the coefficients. And this then is the representation of the vector potential. Now, a slight digression. In the case of mechanical systems, it is customary to talk about what you call the dynamical state of the system. And by definition, this is the information that you have to specify in order to specify the subsequent evolution of the system in time. So in mechanical systems, this could be the positions and velocities of all the particles at a given time. Sometimes we represent this geometrically by creating a space that has axes, position, and velocity. So that a single point in this space, it's for 1 degree of freedom, it's a two-dimensional space. A single point in this space represents the dynamical state of the system, and once this information is given, then there is a unique trajectory giving you the time evolution afterwards from some initial x0, v0 to some final x and v at a later time. Or one frequently uses, instead of x and v, one uses x and p, which is the momentum instead of the velocity. But it's a similar idea, is that the specification of x and p specifies the dynamical state of the system, and so the subsequent time evolution is known. Now, for mechanical systems, you need both position and velocity because the equations of motion are second order in time. For the Schrodinger equation, which is first order in time, you only need the value of psi. You don't need psi dot, you just need psi. But the wave equation for the vector potential is second order. So if you want to know what the dynamical state, or how to specify the dynamical state of the free electromagnetic field, it's not just A alone, but we also need the first time derivative of A. We need partial of A with respect to t as a function of x. If I give these two vector fields as a function of x at an initial time, then I have enough information to determine what the field is going to be at any later time. But just A alone by itself wouldn't work. Now, just as I have this is an example of a mode expansion, which we're going to refine. Just as I have a mode expansion for the vector potential, we can get a mode expansion for its first time derivative. All we need to do is to use this equation for c dot for just differentiate both sides with respect to time. The coefficient c depend on time, plug this in, and we get 1 over the square root of v like this, sum on k, and then we have the mode coefficients minus I omega c sub k e to the I k dot x plus complex conjugate. And then let me box these because this is the mode expansion at this stage of the argument for both A and dAdt, which, as I just explained, gives us the dynamical state of the electromagnetic field. Let me put together A of x and partial of A with respect to t of x, which indicates the collection specifying the dynamical state of the field. It's like a position and velocity for a mechanical system. These C's are, if these C's are known, this is at some given time, if these C's are known, it's obvious I can sum these Fourier series and get the A and the A dot. However, it turns out that the opposite is also true. if I'm given the A's and the A dots, I can find out what the C's are. And the result is that there's in effect, a coordinate transformation on the infinite dimensional state space of the electromagnetic field. It takes us from the A and the A dots to the collection of mode vectors CK. This is one transverse vector at each point K of each lattice point in K space. Now, it's quite clear from these formulas that knowledge of C gives me knowledge of A and A dots. So the arrow certainly works this way. Does it also work the other way? The answer is yes. And let me show you how I'll do this. Let me take this plus complex conjugate here and write it out explicitly. It becomes plus C sub K star times e to the minus I K dot x. Like that, okay? That's what the A series can be written out more explicitly. Now, this sum on K is a dummy variable, runs over lattice points in K space. I can replace K by minus K. Let's do that in the second term because it'll turn the minus IKX into e to the plus IKX, making those two factors the same. So this can also be written, I'll remove this boundary here, this can also be written now as 1 over square root of volume B, the sum on K, and now what I have is C sub K plus C sub minus K, complex conjugated, all multiplied times e to the I K dot x. Okay? That's another way of writing the expansion for the vector potential. However, over here, I was giving you the expansions in Fourier series of an arbitrary field. This was a scalar, but I can promote it to a vector if you want. And if I do this for A, for the vector potential A, and knowledge of the field gives me the knowledge of the Fourier coefficients and vice versa. So knowing S of X gives me the S of K's. So I can write this as the sum on K. Well, there's a conventional factor 1 over root B up front. And then it's the sum on K of A sub K times e to the I K dot x. Now, because A is a real field in real space, A sub K is actually equal to A sub minus K complex conjugated. But the C's don't correspond to any vector field in real space. These are just mode amplitude coefficients. That's all they are. In any case, by comparing these two formulas and using the linear independence of e to the IKX, you can see what we get is that you get a formula that says that A sub K is equal to C sub K plus a C sub minus K complex conjugated. And likewise, from the dAdt equation, we get A sub K dot, vector here, dot. Again, if I know dAdt is a field, I can just do its Fourier series and get the coefficients, which are the A sub K dots. And that's equal to minus I omega C sub K plus I omega C sub K, C sub minus K, complex conjugate. Like that. All right? Now, this is a simple system of linear equations that you can solve. And if we do it, we obtain expressions for the C's in terms of the A's, and it looks like this. So this is C sub K is equal to 1/2 of A sub K plus I over omega A sub K dot. And there's another formula, C sub minus K star, which is actually completely equivalent to the one above. Is A sub K minus I over omega A sub K dot. This is what you get just by inverting these equations, doing the algebra. And of these, the second equation is really just a version of the first equation. The first equation alone contains all the information. And the main point that I want to make here is that what this equation shows is that knowledge of the A's gives you a unique set of C's. So this transformation, where knowledge of the C's implies the A's, it works the other way as well. And this means that these coefficients, which are, they're going to turn into what we'll call mode amplitudes of the electromagnetic field, is that the mode amplitudes are in effect coordinates on the state space of the free electromagnetic field. The specifications of these complex, one transverse complex vector at each lattice point in k-space is equivalent to giving you the complete state of the free electromagnetic field. All right. I erased my diagram earlier for lack of space, but I mentioned that the goal here is to start with the equations of motion, to leapfrog past the Lagrangian, and to guess the Hamiltonian. You not only have to guess the Hamiltonian, you have to guess the Q's and the P's. So this is what we're aiming for here, is that the Q's and the P's are descriptive of the dynamical state of the electromagnetic field. And as we'll see, they come out of the mode amplitudes, of which these C's are an initial version of that. So this is partly aiming towards the Q's and the P's of the field. There's also the question of the Hamiltonian itself, which I probably won't get to tonight. Okay, now, so these formulas, such as these that I boxed here, or the inverse formula, which got boxed, did it get boxed or did it get erased? The inverse formula is, it did get erased, but it doesn't matter. The point is that the formula which I'm boxing here is equivalent to specifying this coordinate transformation on the state space of the electromagnetic field. Now, the further change is convenient. These vectors ck, which are a version of the mode amplitudes, what I'll be calling the mode amplitudes, are transverse vectors. I just explained there's one of those for each lattice point in k-space. So they in effect have only two independent components because they lie in the transverse plane. This makes it convenient to introduce basis vectors in the transverse plane in k-space. So here's what we'll do. Here's kx, ky, and kz. And let's have a k vector going out to some point in k-space. This now should be a lattice point. Let's draw in the transverse plane like this. And allow me to introduce in this plane, allow me to introduce a pair of orthonormal unit vectors, which I'll call epsilon hats of k1 and epsilon hats of k2. We want to use these to expand complex vectors, so we're going to allow these to be complex unit vectors. So in an arbitrary manner, for each lattice point in k-space, let's look at the transverse plane, let's define a pair of orthonormal unit vectors in that plane. These unit vectors have the following properties, is that k vector dotted in, or k hat, doesn't matter, k hat dotted into epsilon hat k mu is equal to 0. The mu index runs from 1 to 2, like this. This mu index, by the way, here, this index there and this index there, we'll call this a polarization index. This mu goes from 1 to 2. And these vectors are orthogonal in the k direction, because they lie in the transverse plane. They're also orthonormal to each other, that epsilon k mu dotted into epsilon hat k mu prime, and we complex conjugated one of them. It's a Kronecker Hilton mu prime. They're orthonormal in the sense of complex vectors, with a star on one of them. Notice that the k values have to be the same in this orthonormality relation. If I have a different k value with a different plane over here, it has its own k vectors, but don't even lie in the same plane. So there's no relationship, no necessary relationship between polarization vectors in one k plane and they are for a different value of k. The k values are the same and they satisfy this orthogonality condition. So this is the basics of polarization vectors. Now, if I do this, then I can expand the mode amplitudes of these vectors, these transverse C vectors, and linear combinations of, and by the way, I should say that you're of course quite familiar with polarization vectors in optics, such as linear polarization. If you have a wave traveling in the z direction, if this k direction is in the z direction, which is how they set it up in simple problems, then the polarization vectors span the xy plane. And you no doubt know that if it's x hat or y hat, you have what you call linear polarization. That's where the electric field traces a line along the x or the y. It follows a line as time evolves. That's why it's called linear. Whereas if you make them x plus or minus iy, you get circular polarization in which the electric field vector traces on a circle. That's why it's called circular. There are also states of elliptical polarization if the k's are somewhere in between these two. There's a whole story about polarizations in optics. Maybe you've been through this in Physics 209. But that's what these are. The only difference from what I just described is that it's pointing in an arbitrary k direction now instead of the z direction. Now, these mode amplitudes, these c sub k's, allow me to expand them in terms of the polarization vectors. So let's take c sub k and write it as the sum on mu equals 1 comma 2 of epsilon sub k mu times c sub k mu. And now there's no arrow over the c because this is a scalar for each value of k and mu. It's a complex number still, but it's a scalar now. And if I simply make that substitution and put it into my expression for A, then here's what we get. We get a mode decomposition for the vector potential A of x and t, or A, just write A of x, it has a time dependence. It's 1 over the square root of volume v. It's a sum on, now it's sum on k and mu of c k mu, epsilon hat k mu, e to the I k dot x, plus complex conjugate. And a similar expression for dA dt, I'll write it as a dot of x. No, I'm not going to write it yet. There's a similar expression for a dot. I'll just leave it out. I'll fill it in something. I'll fill in what I need in a minute. But anyway, this is the transformed expression for the vector potential. Okay, so we identify a combination of a k vector and a polarization vector. This combination of what we call a mode of the electromagnetic field. This is the definition of the mode. And it's convenient to have an abbreviated notation for it, so I'm going to use a single symbol lambda like this to stand for a mode. So we'll call lambda equals k mu stands for a mode. It implies both k and mu. And if you allow me to use my eraser, I'm going to change this sum here to replace the k mu with a lambda here. So we sum on modes lambda like this, c lambda, epsilon lambda, e to the I k dot x. I'm going to fill in the complex conjugate explicitly. C lambda star, epsilon lambda star, e to the minus I k dot x. Like so. And then the a dot then is 1 over the square root of volume v, sum on lambda, and we have minus I omega, c lambda, epsilon lambda, e to the I k dot x, plus I omega, c lambda. It's supposed to be a capital C here, large C, not to be confused with the speed of light, which will be a small c, capital C lambda, complex conjugated, epsilon lambda star, e to the minus I k dot x. And these then are the mode expansions now in which the individual modes, scalar modes in effect, have been identified. You can see that there are 2 modes for each point in k space. Altogether, an infinite number of modes. So this is the mode decomposition. And by the way, the C lambdas have an equation of motion, which is really the same as this equation, except we just project it into the various polarizations. So the C lambda dot is equal to minus I omega C lambda. Those are the equations of motion for the expansion coefficients. And with this understanding, then this solution, solving this gives me C lambda is equal to C lambda of 0 times e to the minus I omega t. And if I were to plug that in here, I'd get the actual time evolution of the light waves. So the time evolution of the light waves has now been reduced to this simple multiplication by a complex phase factor for each of these complex mode amplitudes, one complex scalar for each mode of the field. Okay. E to the minus I omega t. Right. The overall effect of this is to create another coordinate transformation. It's a pretty trivial one, actually, the second stage, but it takes us back and forth between the CK vectors, transverse vectors, over to the C lambdas. And the collection of the C lambdas specifies the dynamical state of the field just as well as any of these other choices do. So we're going through a series of, in effect, coordinate transformations on the phase space of the field, the free field. All right. Now, I have enough time, I think, to make the point now about guessing the canonical coordinates. We need the Q's and the P's of the electromagnetic field, and we need the Hamiltonian. We won't have time to do them both tonight, but I think we can do the Q's and the P's. It works like this. If each C lambda is a complex number, and if you look at the time evolution, it's just multiplied by the phase factor, e to the minus I omega t. So the evolution of each of these C vectors in the complex plane is just a circle. If I have the C lambda of 0 at some initial time, then the C lambda at a later time is just rotated in a clockwise direction by omega t, clockwise because it's e to the minus I omega t. Now, perhaps this reminds you of what we did with harmonic oscillators last semester. You remember that in the phase space of the harmonic oscillator, in which the Q and the P were like the real and imaginary parts of a complex number, the X, we call them X and P instead of Q and P, that the motion is a circle. In fact, in order to make the motion a circle, we needed to scale the Q and P variables in the right way. But in any case, one can make it a circle. And so this looks like the evolution of a harmonic oscillator. And so it leads to the guess that the C lambdas can be written as some constant k like this, which you need to work out what it is. And then otherwise, its real and imaginary parts are the Q's and the P's for a single mode of the field. This is leading to the notion that each mode of the electromagnetic field is associated with a harmonic oscillator, and that these are the Q's and the P's. So if you want to get the Q's and the P's out of the original vector potential and its time derivative, you follow these chains of coordinate transformations, and then you break them up, the real and imaginary parts of the C's this way. Now, this also means that we know what the Hamiltonian is, because the Hamiltonian for a single oscillator with Q and P like this would be, well, we call it 1/2 x squared plus p squared in the notation we were using last fall. So what I'm going to do is just change the notation to what's appropriate here. So we expect the Hamiltonian for a single mode to be omega over 2 times q lambda squared plus q lambda squared. Like this. And omega, of course, depends on k, which is contained in lambda. I can put omega sub lambda here if you want to emphasize that. So then the Hamiltonian for all the modes, which are all independent of each other in the free field, is going to be sum over lambda like this. And this should be the Hamiltonian like that. So we guess the Hamiltonian, but this is the Hamiltonian for the electromagnetic field. And I don't know whether I've got 1 minute left or 0. I think it's 1 minute left. So, what we've accomplished is to carry out a transformation, at least on the free field, and some work also on the interacting field, to the point of making a good guess for what the canonical Q's and P's are for the classical electromagnetic field. And this also leads us to a form for the Hamiltonian. Now, at the same time, the Hamiltonian ought to be the energy of the system, which for the electromagnetic field is going to be the integral over space of E squared plus B squared over 8 pi. And if we combine, as I'll show you in the next lecture, if we combine this information or this guess about the energy of the field, if we guess the energy is the Hamiltonian, combine that guess with this guess for the canonical variables, we can find this k, this proportionality constant which appears here, and then we have filled in all the details. Then one can simply check that the Hamiltonian, in either of these two forms, they're really the same Hamiltonian. You see reproduce Maxwell's equations and the evolution of the light waves. And then if I may add one more thing, I think you can see the next step is then to quantize these oscillators by Dirac quantization, and we have a quantum description of the field you can probably appreciate that these are going to represent the photons in the different modes of the field. So next lecture will be filling in more details of that, including the interacting field, which is more complicated. Okay.